Hey guys, in this video I'm going to run you through everything you need to know about graph transformations involving translations and stretches in both axes. Every section is going to be timestamped so you can easily find a section you'd like to rewatch. Hope you find this helpful. Before we can look at graph transformations, we need to make sure we understand function notation. We can first think of function notation as simply another way to notate equations. For example, we could rewrite the equation y equals x squared in function notation as f of x equals x squared. F is simply a letter I've chosen to denote my function. Whatever's inside the brackets, in this case x, is the argument of the function, or the input. The other side of this equation gives me the output of the function. Let's be clear about how functions work. First, we take an input, then we apply the function to the input. In this example, the function simply squares the input. Let's take the number 2, run it through our function. The output we could write as f of 2, which in this case would be 2 squared or 4. We can represent functions as graphs the same way we represent equations as graphs, simply by assigning the y-coordinate to be the output of the function. That is to say, if we take an x-coordinate for the input, we pass it through the function and retrieve the y-coordinate as the output. Let's take a look at our first graph transformation, horizontal translations. We can translate a function f of x simply by adding or subtracting a constant to the input. As an example, let's say our function was f of x equals x squared. The graph of f of x plus 2 then would be the same x squared graph but shifted to the left by 2. To see how this works, let's first remind ourselves how we generate the points for a graph. First, let's take the x value of 2, run it through the function. That would be 2 squared, or 4, so the point 2, 4 would lie on our curve. Now let's think about how we can generate a point for the graph of f of x plus 2. Let's take the same value of x equals 2, but now we have to add 2 before we pass it through the function. Now we take our new value 4 and pass it through the function, which would give us f of 4, or 16. But now we have to remember our actual x input was 2. So we need to subtract 2 from this x-coordinate to get the point on the graph of f of x plus 2. Now we can see, to generate the graph of f of x plus 2, we simply take every point on the graph of f of x and subtract 2 from the x-coordinate. So to summarize, if we want to horizontally translate a graph, that corresponds to transforming the graph of f of x into the graph of f of x plus a. To perform the transformation, we simply take any xy point on the original function and subtract a from the x-coordinate. Note that if a is a positive number, the graph would be translated to the left, and if a is a negative number, the graph is translated to the right. Now let's look at stretching a graph horizontally in the x-axis. We can stretch the graph of f of x by multiplying the inputs by a constant before passing them through the function. To see why this would produce a stretch, let's use the number line to visualize multiplying a set of numbers by a constant. First, let's take all the integers from 0 to 10. Now, let's take those integers and multiply them by 2. We can see the distance between all the integers has been stretched by a scale factor of 2. Let's apply this transformation again to the graph of f of x equals x squared. If we plot the graph of f of a half x, that would actually stretch the graph horizontally by a scale factor of 2. To see how this works, let's pass an input through the function. First, let's take the input of x equals 4. But for our new graph, we need to multiply the input by a half before we pass it through the function. Now we take our new value of 2 and pass it through the function. Now we need to remember our actual x input was 4, so we need to divide the x coordinate by a half to undo the multiplication we did earlier to get the point on the new graph. So now we can see, to generate the graph of f of a half x, we need to take all the points on the graph of f of x and divide their x coordinates by a half. So to summarize, if we want to stretch a graph horizontally, that corresponds to transforming the graph of f of x into the graph of f of a times x. To perform the transformation, we take any xy point on the graph of f of x and divide the x coordinate by a. For this transformation, it's not immediately clear what it means to have a be negative. To help us work out what this means, let's take a simple function, say f of x equals x, and now let's try to transform it into the function of f of minus x. Using our formula for the transformation we worked out earlier, that would just mean we take any xy point on f of x and divide the x coordinate by minus 1, which would give us minus xy. If we apply this transformation to a collection of points on our graph, we can see that a being negative simply reflects the points in the y-axis. Sorry for interrupting the video, guys, but if you need any extra help with maths, further maths, or physics, you might be interested in having some one-to-one lessons with me. I run all my lessons over Discord, and regular students are welcome to send me questions they have in their studies anytime. To find out more, head over to revisionsolutions.co.uk using the link in the description. Thanks for listening. Let's get back to the video. Now let's take a look at how to transform a graph by stretching it vertically in the y-axis. We can stretch a graph vertically by taking all the outputs from the function and multiplying them by a constant. If we use the same function of f of x equals x squared again, the graph of 2 times f of x would be the same graph stretched by a scale factor 2 in the y-axis. To see how this works, let's pass an input through our function. If we take the value of x equals 2 and pass it through our function, we would retrieve the output of 4. But now, to get the point on the graph of 2f of x, we need to multiply this by 2. Now we can see if we want to generate the graph of 2f of x, we take any xy point on the graph of f of x and multiply the y-coordinate by 2. So to summarize, if we want to stretch any graph f of x vertically in the y-axis, this corresponds to transforming the graph of f of x into the graph of a times f of x. To perform the transformation, we take any xy point on the graph of f of x and multiply the y-coordinate by a. Let's check again what happens when a is negative. Let's take the graph of f of x equals x squared and transform it into the graph of minus f of x. Using our formula for the stretch from before, we take any xy point on the graph of f of x and multiply the y-coordinate by minus 1 to give the point x minus y. If we apply this transformation to a set of points on our function, we can see if a is negative, it reflects the points in the x-axis. Next, let's take a look at translating a graph vertically in the y-axis. We can translate a graph vertically simply by adding or subtracting a constant from the output of a function. So if we take the graph of f of x equals x squared, the graph of f of x plus 2 would be the same graph translated up by 2. To understand how this works, let's pass an input through the function. Let's take the value where x equals 2 and then pass it through the function. That would give us f of 2, or 4. But now to get the point on the graph of f of x plus 2, we need to add 2 to the output to give us 6. Now we can see, to generate the graph of f of x plus 2, we take any xy point on the graph of f of x and add 2 to the y coordinate. So to summarize, if we want to translate a function vertically in the y-axis, that corresponds to transforming the graph of f of x into the graph of f of x plus a. To perform the transformation, we take any xy point on the graph of f of x and add a to the y coordinate. Note that if a is positive, the graph is translated up, and if a is negative, the graph is translated down. Now let's take a look at the order we should perform transformations in. The first transformation we should always apply is x translations. Next we apply stretches in the x-axis, which are also reflections in the y-axis if a is negative. Then we apply stretches in the y-axis, which are also reflections in the x-axis if a is negative. Lastly, we apply vertical translations. If we were to apply all the transformations to the function f of x, it would look like so. As an example, let's take a point on the graph of f of x equals x squared and transform it to its corresponding point on the graph of 3f of 2x plus 1 minus 4. If we take the value of x equals 3 and run it through the function, we would get 9. So the point 3, 9 lies on the graph of f of x equals x squared. The first transformation we apply is horizontal translations. So we need to subtract 1 from the x coordinate to give us the point 2, 9. Next, we apply stretches in the x-axis, so we divide the x-coordinate by 2, which would give us the point 1, 9. Following this, we apply stretches in the y-axis, so we need to multiply our y-coordinate by 3, which would give us 1, 27. Lastly, we need to subtract 4 from the y-coordinate, which would give us 1, 23. Next, let's look at how transforming graphs affects their equations. Let's again use the example of f of x equals x squared. Let's remind ourselves quickly again how function notation works. We take our input between the brackets, in this case x, pass it through the function, and this function squares that input. So now, if we wanted the equation for the graph of f of 2x plus 1, our input is now 2x plus 1. We pass it through the function, which would give us 2x plus 1 all squared. So our equation for the graph of f of 2x plus 1 would be f of 2x plus 1 equals 2x plus 1 all squared. If we'd like the equation for the graph of 3f of 2x plus 1, we simply take the equation for f of 2x plus 1 and multiply it by 3. If we want the equation for the graph of 3f of 2x plus 1 minus 4, we take the equation for the graph of 3f of 2x plus 1 and subtract 4. Now let's consider the general form of a quadratic. For any quadratic, we know we can rewrite this form by completing the square. We can represent this form in terms of graph transformations of the basic f of x equals x squared graph. This means we can think of the graph of any quadratic as a simple combination of transformations to the basic graph of f of x equals x squared. That's the end of the video, guys. I hope you found it helpful. If you did, please drop it a like, that helps me out a lot, and consider subscribing to the channel to find out when I release new videos. Thanks, and I'll see you in the next one.